Okay, this is continuing topic 8.5, so this is part 2 of the 2 videos. So let's do a practice question. How to find the molarity of your unknown. So a 50 milliliter sample of HS, or HF, an aqueous solution of unknown concentration is titrated with 2.1 molar potassium hydroxide. The graph shows data taken during the titration. What is the concentration of the HF sample? So let's take a look at our information we're given. We've got 50 milliliters, so I like to draw just a little sketch of what's going on. I've got 50 milliliters of acid, my acid, HA, or we can now go ahead and write the formula HF. We do not know its molarity, so question mark molarity. It is titrated, so that means the chemical dropping into it is 2.1 molar KOH. And we've got our graph of our titration curve. So we want to know the concentration of our HF sample. So the best way to be able to do that is to be able to find where we have equal moles of our chemicals so that we can get moles of our acid. We've got the volume of the acid, we need its moles to be able to find that value. So we're going to use our graph to figure out how much base did we actually use, what volume of base did we use. So we're going to go to our graph and find our equivalence point, and I would estimate it about here. Since we have HF, that's a weak acid, so that's why we're starting at a higher pH. That's something to note on our graph here. So that's why our pH is shifted up, and I would estimate our pH probably to be around 9. Okay, so at pH of 9, our volume is that first line after 10, so our volume is 11 milliliters. So we've got 11, let's go ahead and add a 0 on that, milliliters of KOH of 2.1 molar KOH. Okay, now to solve this, we can use basically our dilution equation. You guys should remember from last semester, M1V1 equals M2V2. Some people also write it this way, V1M1 equals V2M2. Just so you can think, you have to voom, VM. All right. So you can think about these 1s and 2s. Instead of being 1s and 2s, you can think about acid and base. So one side your acid, one side your base. So if I've got 11.0 milliliters and 2.1 molar, that's of my base. And that's going to be equal to my volume times my molarity of my acid. So my volume of my acid is 50 milliliters. And I don't know the molarity of my acid. Okay, why can we do this? Well, an acid and base reaction is 1-to-1. One hydrogen from our acid is joining with one hydroxide from our base to make our salt and water. So since they're a 1-to-1 ratio, we can use this dilution equation. The dilution equation has molarity times volume. Molarity times volume is moles. So this is saying the moles of my base equal the moles of my acid. And that's true only at the equivalence point. So that's why we use that point on the graph. So to solve, we would divide by our 50 milliliters. And we can leave these in milliliters because the units will cancel. As long as they're consistent, we're fine. So our molarity of our acid is going to be 11 times 2.1 divided by 50, which I got 0.462, and we've only got 2 sig figs, so 0.46 molar HF. All right, so that's how we can find the molarity of our unknown solution. This is the same type of calculation we can do at the regular titration. It's just that the way we're getting our volume of from our burette is from our titration curve. So instead of having to rely as much on us finding a color change with an indicator, we have a graph to help us. So it can be a little more exact depending on how good your graph is. Now, the other thing we want to find is the Ka. And again, this is that half of the equivalence point. So if our reaction happened our equivalence point was at 11. Half of that is 5.5. So we want to find 5.5 on our graph here, follow it up, so that would be here. So then I want to find the pH at that point and estimate it the best that we can. So I would say the pKa equals the pH when it is 4. I'd say that's about 4.8. Maybe 4.7 or 4.8. All right, so if I want the Ka, I'm going to do 10 to the negative pKa. So 10 to the negative 4.8. And I get, let's put that in scientific notation, 1.6 times 10 to the negative 5 is my equilibrium constant for my acid. And we can see that's a pretty common range for our weak acids there, HF. So that's how we can find our Ka value and our molarity of our acid, two really valuable tools to have for a reaction. So now we're going to take a look at how we do a problem, a titration problem, when we don't necessarily have the titration curve. How do we find the pH, the equivalence point, that sort of thing. So it says a student conducts an acid-base titration in an AP chemistry lab. They find 35 milliliters. So let's do some underlining here. 35 milliliters of 0.325 molar CH3NH2. So we can see that at CH3NH2, it's got that NH group. That's a really good indicator that that's our base. So we've got a volume and molarity of our base is required to titrate 0.265 molar HCl to the endpoint. Okay, so we've got a molarity of our HCl. We want to know the initial volume of that acid. We can tell that the HCl is our acid. It's one of our strong acids. So we don't have to worry about figuring out who's strong or who's the acid, who's the base. We know which one's strong. So first we want to find the initial volume of the acid. We'll get to these other questions. So let's just call this question number 1. Okay, we want to know the volume of the acid. Well, we've got a volume and molarity of our base. We've got a molarity of our acid. So we can use our dilution equation. So boom, boom. And I'm just putting A and B to indicate acid and base, so we can keep track of our numbers. So our volume of our acid is what we want. Our molarity of our acid is 0.265 molar. Our volume of our base is 35.0 milliliters. And our molarity of our base is 0.325 molar. So if we want to solve for our volume, we're going to divide both sides by our 0.265. So 0.265. The molarities will cancel, so we're going to be left with milliliters. So we get 35 times 0.325 divided by 0.265. And we get 42.9 milliliters of our acid, which is HCl. So we know our initial volume of our acid. So we can use that equation to find initial volume, initial molarity, those kinds of things for our chemicals. All right, let's take a look at the second question up here. It says, how many moles of acid and base have reacted at the endpoint? Okay, well, if we want to find our moles of acid or our moles of base at that endpoint, then we just need to do a volume times a molarity. We can do it for either chemical. I tend to use the one I'm given both values for just because we have them, but you can use either one. So you could do, let's see, let's just use our base here. So if I want moles, that is equal to my volume times my molarity. Let's do it for our base. So that would just be that 35.0 times, we do need to put this one in liters if we're going to do that. So 0.035 liters, because liters times molarity gives us moles. So that would give us 0.035 times 0.325, and that would be equal to 0.0114 moles. And that could be moles of our acid or moles of our base, because remember, they're equivalent, they're equal to each other at the equivalence point. So how many moles of acid base have reacted at the end point or equivalence point? They should be equal. So that is our number of moles of acid or base. Okay. So now there is a third question. Determine the pH of the solution at the end point. And this is the part that's a little harder. We're going to do that on a new slide. So let me go to my new slide, just so we have space here. And I have an explanation of what we're going to do, because this is where it can get a little trickier. Okay. So it says, so we're doing this part that's underlined, determine the pH of the solution at the endpoint. So if we did this titration and we didn't do a titration curve, this is what we would have to do to find that pH. Now, the reason we have to do this process is because it is a weak acid a weak base and a strong acid, and we have equal moles of them. So we have to do a little bit of a weird process. So to determine the pH, we need to think about the reaction occurring. The weak base has been neutralized at the endpoint by the strong acid. Therefore, there is no strong acid or weak base left in the solution. They're gone. They're used up. However, the reaction produces the conjugate of the weak base. So when our base reacts, we can see that here, it produces its conjugate where we've added that hydrogen ion. Now, that chemical, the conjugate of a weak base or the conjugate of a weak acid, this causes a secondary reaction with the water that's present for these aqueous solutions. And that secondary reaction is going to affect our pH, affect our equilibrium. So we can determine the effect of this on the equilibrium by determining the equilibrium occurring between the conjugate and water. Then pH can be determined. So we can see our reaction there, our normal reaction that took place. And when this reaction occurs, we create that conjugate, so CH3NH3+. So I'm going to take that, and we're going to explore what that chemical does when it's added to water. Okay, because it's hanging out in that aqueous solution. So what happens there? Well, this CH3NH3+, when added to water, that water can grab that extra hydrogen that this thing has, and it's going to create CH3NH2. And when water grabs an extra hydrogen, we get H3O+. Remember, H3O+ is just like our hydrogen ion, but with water. So it kind of breaks it back down and releases some of that hydrogen ion back into the water. So we have a rice table set up. Now, water is always your liquid. We can ignore that section. We don't care about that. Okay? Now, we need some concentration, some things to plug in here. So let's think about what's going on. We already know how much of our chemical CH3NH3 has been made, right? We know that because on the last slide we calculated our moles of acid and our moles of base that reacted. Okay, we found that 0.114 moles of acid and moles of base reacted. So equal moles of acid and base. Well, it's all a 1-to-1 ratio. So if those reacted that much, they're going to produce the same amount of product. So that's how many moles of our product we've made. Now, it's now in a new solution. We've added 35 milliliters to, we calculated on the last slide, 42.9 milliliters. So we now have a new total volume, which is 77.9 milliliters, or 0.0779 liters. So we can find the molarity of that solution. So 0.0114 divided by 0.0779. 0.146 molar. All right, so that is our initial concentration of our product there. And then it's going to react to form these, but they start as 0. Now, we don't know how much is reacting. We're going to use X, 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 and we bring it down. So 0.146 minus X. Okay, so we find, first we write our reaction. So our conjugate, our product, plus water, what does it make? And let me just point one other thing out. So CH3NH3 plus, we had a base, the initial chemical. So I'm gonna erase and start over. So this initial chemical was a base. It formed a conjugate acid. So now this is an acid, so it's gonna act like an acid and give away a hydrogen to water. So that's how we know what we're making in the products. Okay, acids always give away. Okay, now we want to solve for X, right? We've done that before with rice tables. Well, if we want to solve for X, we need a K value to plug in. Let's write in, we can write an equilibrium expression. So this is our Ka because it's our acid reacting. We would have the product CH3NH2 times H3O plus or H plus over our reactant CH3NH3 plus. So that's our expression. Now we don't have a Ka value. If we look up here, we have a Kb value, but we can switch between those two. I'm going to do that over as a side calculation. Remember that Ka times Kb gives us Kw, the equilibrium constant of water. So when you have a conjugate acid and conjugate base, we can switch between their K values using Kw. So Kw is 1 times 10 to the negative 14th. We have our acid. We would have to divide by, we have our base on our acid. So we're going to divide by Kb on both sides, and that would give us our Ka. So our Kw value is 1 times 10 to the negative 14th divided by our Kb that's given at the top, 5.0 times 10 to the negative 4th. So we get 1 times 10 to the negative 14th divided by 5 times 10 to the negative 4. And we get 2.0 times 10 to the negative 11th. So that's what we want to plug in for Ka. 2.0 times 10 to the negative 11th. That's going to equal, we've got x and x on the top, so x squared over, and our value is very tiny, so we can round this to just 0.146 instead of minus x. So we're going to multiply 2 times 10 to the negative 11th by 0.146. We get 2.92 times 10 to the negative 12. I think our bell's going to ring in a second, so ignore that. That equals x squared. And then, of course, we want to square root both sides. And so x is going to equal the square root of that value. And, messed up my calculation here. Okay. So the square root of our answer. Clicked the right buttons that time. And we get 1.7 times 10 to the negative 6th. And that is our x value. Now remember, we're not done. Our whole goal here is to figure out the pH of the solution at the endpoint. But x gives us our concentration of our H3O plus, which is the same as our concentration of hydrogen. So to find pH, we're going to do the negative log of that value. So negative log of 1.7 times 10 to the negative 6th. And we get a pH of 5.77. And that is our final answer. So it is convoluted. It is a longer process, but it's not impossible, and it's just taking a lot of steps we've done before and putting them together a little bit. The new part is having to write that reaction for that new equilibrium forming. And if we look at this, if we think about our pH, we've got a strong acid and a weak base. So our ending pH should be towards the acidic side. So it should be, I knew that was going to ring. So it should be more acidic, and our final pH is 5.77, so it's on the more acidic side. All right. All right, guys, we are going to take a look at this next practice problem. I'm re-recording this one because of some errors made. So if you've looked at a previous version of this video, this slide is now fixed. All right, so let's take a look at our question. We've got 25 milliliters of 0.1 molar HCHO2. We've got a pKa given, so that is a good indication that that is an acid, along with the hydrogen in front. That chemical is titrated with 0.8 molar sodium hydroxide. Determine the volume of sodium hydroxide used to titrate. Let's just start with that first point. Okay, so to find the volume of our chemical used to titrate, we want to, when it says something like that, when it says to titrate, we're assuming it's reaching its endpoint, and that's where we have equal moles of our chemicals. So when that occurs, so let's call this part A, okay? So we're finding our volume of NaOH. So that's where we have equal moles of our chemicals, so we can do molarity of acid, volume of acid equals molarity of base, volume of base. Basically using the dilution equation. So our molarity of our acid is 0.100 molar times our volume of our acid, 25 milliliters. And that's going to be our molarity of our base, which is 0.8 molar times our volume of base. We divide by our 0.8 on both sides. Molarities cancel, and our volume of base, when we calculate, should give you 3.13 milliliters. All right, 3.13 milliliters. So that's not that much, right? We have 25 milliliters of our acid. It only took 3 milliliters of our base to titrate that. But we can see that the concentration of the base is 8 times bigger. You have 0.8 molar versus 0.1. So it's going to take much less of that to get equal moles. So that answers part A. There's the first answer. Let's take a look at part B. Part B, it says and we'll call this part B, calculate the pH at the end point of the reaction. So we want our pH, which means we need to be able to take the negative log of the hydrogen ion concentration, or we need to be able to find a pOH and then backtrack, so negative log of the hydroxide ion concentration. We need to be able to do one of those to get to pH. And it's at the end point. So at the end point, we have equal moles. When we have equal moles, we have to do salt hydrolysis. Dun, dun, dun. So that's the ugly rice table-y one, but not impossible. Okay, I'm going to start by writing our rice table out, writing our reaction out, and then we'll fill in the pieces we need. So let's do our reaction. When we do a salt hydrolysis, start with your weak. Okay, think about how it breaks or how it becomes its conjugate. Its conjugate would be the acid with one less hydrogen, and that's what we're going to start with, the conjugate of your weak. We're going to add water because it's the hydrolysis, and this was our acid. It made a conjugate base. Bases gain hydrogen, so it's going to form back into that weak acid. And a hydroxide is left from water. So that's the beginning of our rice table. Now we can go ahead and cross out our water. We know we have 0 of that to start. And we need to figure out how much initially we had of our conjugate salt. Now we do that. Remember, the salt molarity or moles are equal to your moles of acid or moles of base, either one. I'm going to do the acid. So we've kind of started that here. So molarity times, we'd have to do liters. So 0.100 molar times 0.0250 liters. We do need it in liters since we're doing just molarity times liters, giving us moles. So that gives us 0. And I actually did this part incorrectly. Hold on a second. All right, I knew my notes were a little bit off. Just wanted to make sure I had all this correct for you guys. Okay, 0.0025 moles of our acid, which means that's the moles of our salt. And when we pour the solutions together, and the reason why that works is because all the acid has turned into the salt, so they're equal molar. We're going to divide it by our total volume because everything's poured together. So we have the 25 milliliters of acid plus our 3.13 milliliters of base. So that'd be 28.13 milliliters, so 0.02813 liters. And when we divide that, we get 0.089 molar. So there's our initial concentration for our salt. All right, we've got our rice table. We're going to go ahead. We use our X's for these because we're trying to find that concentration at equilibrium. So our main goal is to find this X value so we get our hydroxide so we can then find POH and pH. So we've got our rice table set up. Because this is a basic solution, we would need Kb. We write our expression, CHO2, we have hydroxide over CHO2 minus. All right, now our Kb value, we don't have Kb, but we have some things that can get us there. So we have pKa. So on your equation sheet, it has this equation, pKa plus pKb equals 14, just like pH and pOH equal 14. So we can subtract from 14, and our pKb, so pK of the base, would be 14 minus 3.74, 10.26. And then get rid of the P, right? Just like we would undo pH, undo POH, all of those. We're going to do 10 to the negative 10.26. And so our Kb would be equal to that. So that equals, sorry, I'm doing it all kind of up in the extra space there. 10 to the negative 10.26 gives us 5.5 times 10 to the negative 11. All right. So I'm going to plug that in. I'm going to change my color here so we can see where we're at. So 5.5 times 10 to the negative 11 equals, of course, we have x squared on the top. Sorry, that's a square. And this would be 0.089 minus x, which we can assume is 0.089 because that K value is so tiny. All right, so we're going to get x squared. We're going to multiply that 0.089 times our 5.5 times 10 to the negative 11. We get 4.9 times 10 to the negative 12. And we're going to square root both sides. We get our x value. My calculator, not in scientific notation. There we go. 2.2 times 10 to the negative 6. Whew. I know these are long. These are marathon problems. Okay. So we found our x value. We found this, which means we can do a negative log of it. Okay, I'm going to do this in new color here. Find our pH. All right, so we can find POH
by negative logging our x value, so negative log of 2.2 times 10 to the negative 6. And our pOH would be 5.66. So pH would be 14 minus 5.66, like we've done so many times, 8.34. Whew. Okay, so let's think about this. Does that value make sense? Well, we are at the equivalence point. We are at the equivalence point of a strong base and a weak acid. So because it's the stronger thing is the base, it should be a pH that's closer to the basic side, or on the basic side, which this is. 8.34 was above 7. So our equivalence point should be above 7. So that one works.
Okay, this just gives us a quick summary. So we have one on our titration curves. So if we have a strong acid and strong base, they're going to have a pH at the equivalence point of 7. So this is our example titration curve. So this would be a strong acid titrated with a weak base. So we start with the acid, we end with the basic. And then for a weak base and strong acid, so if our weak base is what we're starting with, and we'd start high and we're going low, its equivalence point is going to be less than 7 because the acid is stronger, so it's going to shift towards the acid. We can determine the pH at the equivalence point. We use the reaction of the conjugate of the weak base reacting with water, solve for X in our rice table, then find the pOH and the pH. And then similarly, if we have a weak acid and a strong base, just like we saw in the last slide, we're going to do that same type of thing, but we're going to have a pH at the equivalence point that's greater than 7 because we have that strong base. For both of these, we can find our pKa or our pKb. We do that with half of the volume at the equivalence point, or we call that the midpoint here. We do that. So we find the volume at the equivalence point, we call that V. We cut that in half, so half of V. We go up and find the pH at that point, and then that's going to equal our pKa, and that'll be for both of these. So that's a quick overview of how we can use these, so it's a good little reference for you. Like I said, I'm sorry this video is so long, but it's a lot of info, a little bit longer problems. You guys got this.